All right, welcome to CS. Which one is this? 3510. This is algorithms. So no one can spell that. That's okay. Algorithms. What is algorithms? Well, first off, we're in a course in algorithms. So let's talk about the course first. So this is the summer semester. So normally fall and spring, it's like 75 minutes twice a week, but you have 13 weeks. In the summer, we're accelerated. We have 10 weeks. So we actually have 4 hours of lecture a week. Each class is 2 hours and 10 minutes. But nobody really has attention for this. So what we do is instead we do 1 hour, 10-minute break, which is a pretty good break, I think, and then another hour. So right now we started 12:30. We'll take a break in an hour for 10 minutes. We'll come back, and then we'll do another hour of lecture. And the way things are also going to be done is that they are recorded. So right now I'm recording. If you say something, it might pick you up. That's fine. I expect you to ask questions and so on, and you're going to be on YouTube. Everyone, also, you need to subscribe to me on YouTube. Open my YouTube channel and click subscribe. There are ads on my videos until I hit 1,000 subscribers. So I'm also going to have a backup solution until I figure this out. But in the meantime, please just subscribe to me on YouTube so I get enough. I have 460 something subscribers, so I need 1,000 to. Anyway, yes, the class can be done fully remote as well. Like I don't expect you to come to class, but people who do come to class have on average 12 points higher, which is over a letter grade. So like if you want, think of it like a 12-point bonus if you come to class on average, right? So I don't expect you to come to class. There's like 93 people here. Some people are also taking this course remotely, you know, international travel and so on. The setup of the course grading-wise is there's going to be a weekly homework. Those are worth, I think, like 20%. There's going to be what's called a worksheet, which is also like a homework, but it's due after like 4 hours. So it's like due that day, something like this. And those are 8% of the grade. And then there are 3 or 4 exams, I believe 18% each. So each exam, and then in fact there's not one dropped this semester, but they are not cumulative at all. They're just for that unit. And thereafter are 4 main units. The 4 main units in this class are divide and conquer, and we'll start on that later today. Graph algorithms, traversal, things, very simple stuff. We'll talk about dynamic programming, which is a made-up word, but it basically means like writing down solutions to small subproblems and then recalling those solutions in order to solve larger problems. And then we have a unit on NP completeness, which is basically a lower bounds, like proving certain problems cannot be done faster than exponential time, something like this. There'll also be adjacent units on max flow min cut, on greedy algorithms, and things like this. So this is sort of the outline of the course. Are there any syllabus level questions before we talk about the next thing? Yes?
So you mentioned that it's taken like remotely, right?
Yeah.
So how long does it actually have to like?
Oh, they're just like given to you remotely, and then you take it remotely, and then you upload it remotely. But that means they're harder. So something to think about. Sure. I haven't decided if it's open internet yet, but it's definitely open note. So, yeah. Algorithms is about solving problems. So we're going to give you like hundreds of problems. There's going to be problems on the homework. There's going to be problems on the practice exam. There's going to be problems on EdSTEM. There's going to be problems in office hours. There's going to be problems on quizzes, and then problems on the exams. So the way you learn algorithms is just by doing 1,000 problems. And once you do 1,000 problems, you can convince yourself that, yes, I've learned algorithms, right? Before we talk more about the content of algorithms, I can introduce the TAs who attended today. Some people are not here remotely, of course, but you guys want to come up and you want to say hi and immortalize yourself on the YouTube video, right?
Hi, I'm Griffin. I'm a first-year master's student.
Hey, I'm James, coming up on my 5th year of undergrad.
Hi, I'm Yunjie. I'm a PhD student in cybersecurity.
All right, thank you guys. Yeah. TAs for this class are always an extreme group of people. Whenever I'm looking at resumes, it's completely dumbfounded that these are real. And this is true, of course, fall, spring, summer as well. It's always unbelievable the kind of these people are not human in the sense of their ability to solve problems. So please rely on them for many, many things. Not just algorithms questions, but also like career-oriented questions on like what have they done to get here. Which is the segue into the next thing, is like, why should you learn algorithms? What's the point of algorithms? There are two answers. The first answer is a better one. It's like, algorithms is timeless in the sense that it's in the theory itself is timeless, right? You'll never be outdated. Computer science is a relatively new discipline. It's only like 50-something years old, and biology is a few hundred years old, mathematics is a few millennia old, and so on. So we're pretty new at how to even teach this. And the schools that did really well early on were not the schools that taught COBOL and Fortran. They were the schools that taught foundations. They were the schools that taught theoretical computer science, because these are concepts that don't change. You get a degree in computer science, but all you learned was Fortran. You don't evolve much when you get out of the system. So the principles you learned here are going to stay with you forever, and there is no software update. There's nothing that's going to change anything significantly about the concepts you learn here. And in that sense, they're universal. If you think about an alien, if you discover some sort of species of aliens and they have their own computers and their advanced civilizations or whatever, they would have a version of Dijkstra's algorithm. They may not have a version of PGP or the x86 instruction set, things like this, right? That doesn't mean that practical things are unimportant. They are as equally important. Systems is as important as theory, but the concepts would translate almost immediately, right? So that's the first more important reason that you should learn algorithms. The second reason is that you could make a lot of money. So like, it shouldn't be this way, but unfortunately the way that all the companies with the highest salaries have structured their interview process is that they ask you 4 lead code hards, and then you just like end up with $290,000 salary. I get to look at salary sheets. I have my TAs go out and they collect problems, and we talk about their interviews, and then they go out and they get jobs and stuff like this. So I've seen this happen a lot, and then you wouldn't believe the numbers that I've seen that people are earning. And of course, that some of you are here just for the money, and that's why you want to learn computer science for the money. And there's nothing wrong with that. But in order to pass this interview system of you do 4 lead code hards and then a behavioral interview, you need to get really good at algorithms. You need to become second nature, oxygen you breathe. Now there's of course a whole discussion we should have is, should the system be set up this way? Should society be structured in such a way that you get these high paying jobs if you can solve random balloon popping problems or whatever? The answer is probably no. But we're not here to change the rules. We're here to help you beat the game, so to speak. So a lot of times you leave this class. If you take the knowledge you're supposed to get from this class, you can sleep through any interview, and you just go and. One time we made a final just off of interview questions that people came and brought back to us. It was just like the Google interview questions, what was it, Capital One, whatever. That was the final. And if you say you can't do well in that final, then maybe that reflects how well you can do in an interview, something like this. So it's not supposed to be an interview prep course, but it accidentally becomes really accurately well suited for such a topic. So kind of what happens there. Yes, so time is. More questions on the syllabus, on what is algorithms, on these things, right? Okay, I guess we can just begin. So you guys come with a really good, Frederick in 1332, I think, runs you guys like the Navy, and I'm always impressed with the students that come out of data structures. So you guys have already started some of training in this way, really. And what I will say is also that algorithms this 3510 is not a data structures course. And learning algorithms is also learning how to speak the language of people who do algorithms. And there are certain things that I think students pay focus on that they don't really need to. And then there are other things that should be focused on more. And a lot of times, especially in this class, we'll do pseudocode, but it's not up to me to like implement the pseudocode. That's like up to you in an eventuality. We're working with concepts that are a little more esoteric or something that's like someone else could implement this, but we're not really going to focus too much on that. So there are comments we could make about every algorithm we'll talk about that implementation details can speed things up by a constant or so, but that's not really the focus of the class. And focusing on what's important is, I think, something everyone learns in the first 2 weeks, something like this, right? So let's begin. Any questions on the syllabus, on the structure of the course, on anything like this, anything related to the content? Okay, let's begin. So let's just talk about a motivating problem, which is the Fibonacci numbers. These numbers were not invented by Fibonacci, but we named it after him so we don't hurt his feelings. They've been used for several millennia before him, but they are defined according to the following recurrence. We have f of 0 is equal to 0, f of 1 is equal to 1, and that for n greater than or equal to 2, we define f of n to be equal to the sum of the two previous numbers. Right. We spend a lot of time, at least in my section on 2050, we spend like accidentally somehow like 2 lectures on Fibonacci numbers. And they have a lot of interesting structure and a lot of interesting things. And suppose we're concerning ourselves with writing an algorithm that would compute the Fibonacci numbers, right? Well, obviously we have a definition of the Fibonacci numbers. Let's just compute the Fibonacci numbers according to the recurrence. This, again, this part of the lecture is just a motivating example. We're going to show several ways to write an algorithm for the same thing. So let's say f1, it takes as on input n. If n is equal to 0 or 1, we're going to just say return n. By the way, good pseudocode doesn't need to be, if you're asked for pseudocode and you turn in something that's very language specific, that's not very good. In certain cases, you can get docked points off. Pseudocode should be a few things. It should be extremely easy to read. It should be obvious to analyze the runtime, and that's basically it. It should be as clear as possible. Sometimes we've seen people turn in code, and maybe it brings in obscure data structures or something. It imports a random library. Who knows, right? So writing good pseudocode is also a habit that you'll learn in this class. Else, we're going to return the sum of the two previous, which is f1 of n minus 1 plus f1 of n minus 2. Right. So this is is there any disagreement that this algorithm computes the Fibonacci numbers? So we all agree this computes the Fibonacci numbers, but why? Maybe we're not good at open-ended questions. Yeah? Yeah. Yeah, I mean, then the answer is, maybe it was actually a poor question on my part, because the answer is that's just the definition of the Fibonacci numbers. So obviously it computes the Fibonacci numbers. In general, if we want to, when we're concerned with algorithms, there's 2 things we're concerned with. First off is the runtime, efficiency. We'll talk about that in a second. The second thing we're concerned with is something called correctness. And the correctness of an algorithm is like, does it do what we think it does? Now, when we're working at the low level, the answer is obviously yes. This does obviously compute the Fibonacci numbers. But as we get into more advanced and harder examples, it's not obvious that this specific piece of code solves the problem that we claim it does. That's not always the case. So we want to sometimes make sure that it does so. And sometimes you can supplement that with a mathematical proof. So suppose I wanted to prove that this code computes the Fibonacci numbers. What proof technique would I use? Induction. For most recursive algorithms, by the way, you're going to use proof by induction. We're not going to really focus too much on proofs of correctness, though, because a lot of times, for some of them, they're obvious. When an algorithm is non-trivial on the correctness, we're like it's not obvious that it works. We will do a proof of correctness. But this one is too obvious to do a proof of correctness. Here's the proof. Base case. Everyone recalls proof by induction. Base case, 0 and 1, return n. OK, that's exactly what it is. Now assume by strong induction that these functions return correctly. Then the nth Fibonacci number is simply the sum of those, which is returned, QED. That's what the proof of correctness would look like. Don't even bother writing that down. I mean, it's so obvious that it works. But the cool thing about using induction or strong induction for proofs of correctness is you get to just assume this whole part works correctly. No more questions. That's true by the induction hypothesis. And we'll mention this proof by induction for recursive algorithms thing later. Right? So what's the runtime of such a code? Okay, so obviously it's correct. It's simply, in fact, you could even just say it's correct by the definition. What's the runtime of such a piece of code? Well, it's a little difficult. Let T of n be the time it takes to run this code on input n, right? So there's a bunch of stuff going on, but actually we see that we have a recurrence. It's actually a function of the recursive calls of size n and n minus 2. And then there's some other stuff going on. There's like some case switching and stuff, and we need to know how long that takes. So let's just call it 20. Okay? Doesn't really matter what the constant is. Second comment we actually have to say here, what is the runtime of an algorithm? What is the number of steps? What does that mean? Like, so there's two versions of every program. First off, you take the code, you give it to the computer, you hit compile, it compiles it to the x86 assembly or whatever, and then you can consider the number of steps as the number of literal executed instructions, which could be the literal number of cycles needed per gigahertz of whatever, something like this. So we don't want to measure like time in a stopwatch sense, where you just hit start and stop and see how long that takes. But because if you have a faster computer, of course you can solve the algorithms faster. But we don't want to study computers, we want to study algorithms. So we don't really do it this way. That's why we count number of steps instead of like, let's say, a literal stopwatch time. Yes, so the first idea you can think of is like, you can count the literal number of execution steps. But that's when you actually run the program. When you read code, you're not running it on an actual computer. What you're doing is you have a mental model of the code and you're actually running it in your mind, right? There is no heap and alloc and things like this in your brain. You're just kind of like mentally computing it and understanding how the code works. And in that sense, it's more of an ideal thing. And it can be ambiguous about what takes a number of steps. But you should have good formal training in this already. You should know, for example, how to do a worst case analysis. You have 2 nested for loops. Okay, that's going to be n squared, that kind of stuff, right? That's basically what we're measuring the time here. And when we have a recurrence like this, we could say the time of this call is just going to be time of this plus some constant stuff, right? Now what that actual constant is, I don't actually know. But all that matters is that it's kind of independent of n, right? So we have such a recurrence, and we see that the time looks like this. Now we don't like this. We don't want a function to be a recursive function. We want somehow it to be just something nice, like n squared or 2 to the n or n cubed or something we can look at and make fun of. So how can we can heuristically there's a few ways you could do it. If you take in combo, you might have dealt with recurrences like this, and you figured out a way to find the closed forms and so on. But you can always just kind of overestimate and get a good bound, right? So the first thing to note is that the runtime of the algorithm is monotonic. Do you agree for all n that t of n minus 1 takes longer than t of n minus 2? Why? Yeah.
Because in order to get the first one, you have to do the second one?
For this specific algorithm, yes. So you have to, notice that when you run it on input of n minus 1, it's going to have to call n minus 2 at least, and so on. So in fact, the Fibonacci numbers themselves are monotonic. And by monotonic, we mean the function looks like this, not like this, right? Most runtimes of algorithms on bigger inputs take longer. So most things look monotonic. They never go down. They're always going up, right? So if this is true, then we can combine these two facts to get that t of n exceeds 2t of n over 2 plus 20. Do we agree? Okay. Now we can replace this again, though. We can get a 4 of t of n minus 3 plus 20. Right? You could repeatedly go back down, and what you'll see is that t of n will quickly exceed 2 to the n over 2, right? Eventually, you'll base case out of this. Every time you subtract 1 off the input, you essentially double the time it takes, right? You say ... you extend the idea, you get back down to this level. Now, here's the problem. This is really bad, right? This is we would call this exponential runtime. This is really, really bad. So this algorithm is, in fact, incredibly slow. But maybe you kind of already knew that and kind of expected it to be like that. Let's look at the execution of this algorithm on on input n, right? We call f of n, it's going to call f of n minus 1 and f of n minus 2. Then on that recursive call, f of n minus 1 is going to call f of n minus 1, excuse me, f of n minus 2, f of n minus 3. And f of n minus 2 calls f of n minus 3 and f of n minus 4. And this is going to call f of n minus 3, f of n minus 4. This calls f of n minus 4, f of n minus 5. This calls f of n minus 4, f of n minus 5. And then that's going to call f of n minus 5, f of n minus 6. The point is, it's tedious for me to write this out because the algorithm itself is quite slow. But if we look at the recursion history of the tree, this is like this calls these recursively and so on, right? We notice that actually a lot of it is repeated, and we don't really need to compute this. This whole thing is exactly the same as this thing, right? So why write that down? Why recompute that twice? I'll tell you as well that the difference between the reason we care about algorithm efficiency is not simply to save a little bit of, your AWS credits or whatever. The difference between like a fast algorithm and a slow algorithm can mean the difference between solving a problem and not solving a problem. Because this specific code is so slow, I was curious how long it would take on a reasonably sized input. So I ran f of 1 on input 70 on a server in some back corner in the CCB building, and it took 43 days. The logs show it took 43 days, but it did not finish. Somebody had unplugged it. So the server had turned off before it had finished computing, even. So solving the difference between a fast algorithm and a slow algorithm is not the difference between saving a little bit of money or saving a few milliseconds. It's really the difference between like solving a problem at all or just not solving, just never getting an answer, And that's a really practical consideration, right? Any questions on this part so far? So if we wanted to speed up the algorithm, what could we do? Yeah. Yeah, and in fact, when you compute Fibonacci numbers with pen and paper, you don't do this. You don't do this. The computer's stupid enough to not stop doing this. But if you tried to do this, you would immediately be like, oh, wait, actually, I already wrote that down. So the computer doesn't know to stop, though. It just does exactly what you tell it. So we could give a different algorithm that when we compute the Fibonacci numbers with pen and paper, we don't actually use the recurrence. We write them out procedurally and then compute the next one as the sum of the two previous, right? What are the Fibonacci numbers? 0, 1, 1, 2, 3, 5, 8, 13, right? Something like this. So I computed that one as the sum of the two previous. I didn't compute this 13 as recursively doing something like this, right? So that gives us a second algorithm for Fibonacci numbers. Call it F2 on input n. If n is equal to 0, return n. Excuse me, yeah, return n. Take the array is going to be, we're going to allocate it to n plus 1 zeros. And this is a Pythonic thing. It's not totally like pop quiz, how many of you can read that? How many know what that notation means? You don't. That's okay. I don't fully expect you to. I'm going to explain it. It's just a shorthand I use because I'm a Python guy. When you multiply an array by a number, it just allocates an array of that size, all zeros. So this is going to be 0, 0, 0, 0, 0. It's just going to fix the memory for us. But of course, that's unclear. So I'm going to comment it. It's going to be allocate R equals array of n plus 1 zeros, right? So these are where our answers are going to be stored, right? Then we have our base cases. Array of 0 is going to be, hopefully that we will write down f of 0 in that spot. That's going to be 0. Array of 1 is going to be 1. And then we say we want to make sure that in the array that the next, from 2 onward, it's the sum of the two previous. So we're going to say for I in range, and we'll say 2 to n plus 1, because the array is indexed from 0 to n, we'll say array at I takes an array at I minus 1 plus array at I minus 2. right? Return array of n, because that stores the nth Fibonacci number, right? This is how you compute the Fibonacci numbers with pen and paper. Are there any questions on the algorithm before we analyze it? Okay, first off, is it correct? Yeah, I mean, two things. We could either pretend to do a proof by induction again, or like, okay, well, that's, if this is correct, then that the n minus 1 and n minus 2 Fibonacci number are correctly stored there, and then we sum them to return the answer. So obviously it's correct. Another thing is, I don't really need to do this base case if you think about it, because it's already indexed to 0. So why did I write array of 0 equals 0? It's for clarity. You don't, when you're communicating this to someone, not just a TA who's grading it, or like if you were to do research in some sense, communicating this to whoever's reading your paper, you want to make things as clear as possible. And it doesn't save any, it doesn't waste any time to leave a line of code like this in, even though you know it's already 0 allocated, right? It's been zeroed out. So it is correct, right? Now, what is the runtime of such an algorithm? Yes? I knew someone was going to say this because I say this every time. Where are you getting the O of n from? There's one for loop. So this loop runs for n steps. But how long does this line of code take? It is. The array access, let's say, does take O of 1. So there's an array access, there's a write, and there's a sum. I guess the reason I'm mentioning this is that it's a convention, but it's not always true that addition takes constant time. Addition does not take constant time. Addition of 32-bit numbers takes constant time because you have a circuit and you can just like do that on the CPU like instantly. But what happens if you're adding numbers of 1 billion digits? You can't put that in a 32-bit number. You use a big num library, and then that 1 billion digit number is stored in several different registers, right? That are each 32 bits, and then it's actually 1 billion divided by 32, which is nothing. I mean, that's still a billion, right? So in terms of big O, adding n-bit numbers takes at least n bits, because you got to loop through the bits. So, and this is something we'll explore more. We'll have a lecture on arithmetic. But conventionally, this does not take linear time unless you want to compute a Fibonacci number that's less than 32 or 64 bits or whatever. But in general, we never consider it like this. When we consider algorithms for numbers, we consider them as a function of the number of bits. So it is one for loop, but it takes at least linear time to add them. And in fact, it's known the Fibonacci numbers are kind of exponentially sized. What that means that to write down the nth Fibonacci number takes approximately n bits. It actually takes like 0.7 times n bits, something like this, but it's at least linear. So in fact, this is O of n squared. Right. So two other things I can mention. In terms of practical considerations, yes, we know that n squared is faster than 2 to the n over 2, but by how much faster? I mentioned that one, I ran it on F1 of 70, and it took 43 days. This one I ran on F1 of 70, and you hit enter on the terminal, and the answer pops up immediately before you even have time to finish. In fact, I couldn't, at least with my keyboard, find an input big enough that would have this slow down a considerable amount. It appears instantaneous on any input I would care about. That's really the difference between a slow algorithm and a fast algorithm, is does it work or does it not work? It's not a microscopic improvement. It's like solvable or unsolvable in some sense, right? The second thing I can mention is that there are different regimes, and maybe you are familiar with this. There are different regimes. When you talk about algorithms, you have to talk in the discourse of the algorithm itself. Like, what are we talking about? Because a lot of times there are many letters and stuff that goes around it. It's kind of confusing. So some of the regimes are like sorting. Right? Sorting, when you talk about sorting, what do you measure the algorithm runtime in? Yes?
The size of the set you need to be sorted.
Yeah, it's the number of elements. But each of those elements could be really big, right? You could have an element of your array be 1 billion digits. But that just makes it ugly. What's the fastest runtime you should know for sorting? Yeah, it's n log n. We'll talk about that after the break. Right? But n here is the number of elements. It's not the size of the elements, right? So if you were to say you want to measure the algorithm runtime in both the number of elements and the size of the elements, you would have something really ugly like O of m, n log n, mn something, I don't know. Right? And then you have two letters, and you guys all know from calculus, you have multi, it's really ugly. You can't compare functions nicely, right? So you want to just like fix everything else and then consider the growth of the problem in one specific area. So for sorting, you consider the number of elements, but then you say the elements themselves are fixed. For number algorithms, that's not the case. It's a constant number of numbers you're working upon, but then it's the number of bits of each number. So in this context, and we'll see later, algorithms for addition and multiplication do not take constant time, and there are some algorithms that are faster than others for multiplication. What are some other, these are, you could call these regimes, right? If you're considering a graph, you can, we'll talk about that later. But just know that for each domain you're working in, you have to understand the context of what you're actually measuring things in, right? Any questions on this so far? Okay, let's do a quick review of Big O. Actually, I have some more Fibonacci algorithms for you. So some of you may or may not know that you could actually, everyone should have taken linear by now, right? Everyone know what a matrix is? Everyone know what a matrix product is? Right? Consider the following. Consider this matrix. If I were to do that matrix vector product, what is my output vector? Okay. Now let's say I take that same vector and I multiply it by the matrix again. Okay. Now let's suppose I took the initial vector and I multiplied it by this matrix n times. Almost. This one, so look at the rows. This row is going to propagate this answer up here, right? And then this one is going to be the sum of the two previous. So in fact, this simply computes the Fibonacci numbers. Simple matrix, but it's as simple as the definition of Fibonacci numbers. You multiply this vector by this matrix n times, you're going to get your nth Fibonacci number, right? It's a little difficult to measure the time this takes, but we can try to, we don't know what the time complexity of a matrix multiplication or a vector multiplication or any of these things take. But let's suppose we were trying to compute the nth Fibonacci number this way. And instead of considering the runtime, we consider the number of such operations. How many matrix multiplications would there need to be? Yeah. Yes. You compute n minus 1 matrix multiplications. How many vector multiplications? Matrix vector multiplications. 1. Plus anything else? Let's just say 1 stuff. You read that last element. But is that the only way to compute the nth Fibonacci number this way? And again, we don't know the time of this, that these take, but we can make trade-offs, right? There's another way, given this identity for the Fibonacci numbers, there's another way to compute the nth Fibonacci number. Think if you multiply these in a different order.
Just keep transforming the vector.
Yeah, I guess what I'm trying to ask is like, instead of doing matrix vector, do matrix vector, matrix vector, matrix vector, matrix vector, right? instead of doing AAAV, do it like this. AV is going to give you a vector, that's going to give you a vector, that's going to give you a vector, right? So you're actually going to, you can do 0 matrix vector multiplications or, what is that, n matrix vectors multiplications, right? Which one is better? It's hard to say, but the moral here is you look at the problem from a slightly different angle and you can get a faster solution, right? I'll tell you that a matrix vector product you probably can guess is faster by an entire linear factor than a matrix-matrix product. Matrices are big, matrix vector, a vector is small, right? And in fact, you can even improve this further, right? Do you guys remember diagonalization of a matrix, right? So what we could do is we could take this matrix 0, 1, 1, 1, and we can write it as a product of 3 matrices P, D, P inverse dP, so that when we take the nth power of it, that's actually equal to P inverse dP to the n, which is just going to be P inverse d to the n P, right? When you expand and then they cancel each other out. And then D is simply going to be a diagonal matrix, which has this nice property that d to the n is just lambda to the n, right? So now we're not doing a general matrix vector multiplication. We're just doing a single number's exponentiation. So what is that going to be? That's going to be T of n is going to be 1 matrix vector plus 2 matrix matrix plus 2 exponentiations plus 1, something like this, right? But then that makes it also harder to analyze because if you're considering the bits of these numbers here, you know, does this take faster or shorter than the other one, right? One more I can tell you is, in fact, when you come to this one, you don't actually, if you're considering multiplying all the matrices first, you don't need to perform n matrix multiplications. You can actually multiply n objects faster than multiplying them all together at once. How could you do this? Can you reduce the number of matrix multiplications in this first line here? How?
Use powers of 2, so compute m squared and then m4 and then m8 using.
Exactly. Yeah, you could do something called repeated squaring, which allows you to achieve exponentiation of a large number very fast. So let's suppose you had a to the 17. A to the 17 is just a to the 16, right? Plus, so it's a to the 16 times a. So what you would do here is you would take a, you would say a takes on a times a. And then you would do that how many times? Yeah. Right? 4 times. And then you would just have, at the output, you would have a would be a to the 16. Then you do a single matrix vector product, and then you're done. How many matrix vector products does that, excuse me, how many matrix matrix products does that take to repeatedly square? It's not n minus 1, it's what? Yeah, bases we won't, log bases we won't care about usually if they're on the ground, but then you can improve this with such an algorithm, and we'll talk about fast exponentiation later on. But you can improve this to log n matrix multiplications, right? Okay, I'll give you one more way to compute the Fibonacci numbers that's also equally hard to compare and contrast, but notice that these matrices are fixed, right? The only thing that would change in such an algorithm is this value n here. So the rest of these could be kind of fixed. If you could figure out a way to, first, let's say you could figure out a way to expand this, not that you plug in n and then you do the multiplication, but you do the multiplication first as a function of n, and then you evaluate the n. If you were to do such a thing, it would actually just give you a formula for the Fibonacci numbers. And if I did this in 2050, but does anyone remember what the formula is? Yeah. That's the recurrence for the Fibonacci numbers. I'm asking for the closed form of the Fibonacci numbers. Okay, you should know this. It's just trivia. It's 1 over the square root of 5, 1 plus the square root of 5 over 2 to the n minus 1 over the square root of 5, 1 minus square root of 5 over 2 to the n, right? Now, there's two significant things about that formula. One, it's complicated looking. So it's hard to measure, like, is it fast? Does it work? But the significant thing about it is that you don't need to actually compute any of the previous Fibonacci numbers to compute the nth Fibonacci number. Although it's faster to do so, computing the nth Fibonacci number requires computing all previous. What if you just wanted to jump to the billionth Fibonacci number? Turns out you can. You can use such a formula to compute the billionth Fibonacci number, and you could prove such a formula is correct by induction. But it's then difficult to analyze the runtime complexity of such a thing. A computer can't really do square roots nicely, right? So is this a useful formula? I can leave it to you as an exercise to analyze bitwise if this is faster than any of the algorithms that we've mentioned. But the moral here from this example is twofold. First off, more math can make non-trivial algorithms. A lot of times algorithms have sometimes there's always an easy solution. You just brute force it, or you just kind of like randomly guess it, or you just kind of walk around. That works surprisingly well amount of the time. But those algorithms are usually naive and slow, cubic time for a lot of things. If you want to improve yourself from, let's say, n squared to like n log n, that usually requires a non-trivial mathematical understanding of the problem. And the more math you can bring in, the faster you can speed up the algorithm because the more you can understand about the problem that's being solved, right? That's kind of the moral here about all these weird runtimes that we can't really even analyze. They're even difficult to compare. But then if we were able to actually have a runtime of matrix multiplications and vector multiplications and so on, then we could do this. In fact, we could say sometimes one is better than the other and so on, right? So sort of that's the whole theme of the class. The more math you can bring in, the more non-trivial understanding you have of a problem, the faster you can solve problems. And that's really the difference between, algorithms and programming, is that kind of math. Any questions on this? Okay, let's go on to Big O. We're just going to do a quick review of Big O. You guys should have a really strong understanding of Big O already. The reason we use Big O is, again, because we want to study something that is independent of any computer. They always were making new computers. New computers are faster than old computers. We don't want to study computers. We want to study the algorithms. So that's the reason we use Big O. We say if f and g are two functions, let's say from the naturals to the positive reals, we say f of n is O of g of n if there exist constants c and n naught such that for all n that exceeds n naught, that f of n is less than or equal to c g of n. Right? This is the classic definition of Big O that we all know. Does anyone not know this? Everyone remember this? Right? Several classes you should have seen this: 1332, 2050, 1301, 1331, everything. Right? The reason we care about Big O, though, is that it hides all the parts that we really don't care about. It's really difficult to study. It's really difficult to even study what a computer is because they're so different. There's so many, especially back in the day, there were so many weird architectures and weird things people were doing. So it made it difficult to compare and contrast different problems. But we don't want to study all these alien devices that people were coming up with. We want to study specifically code, algorithms themselves, which is independent of any specific implementation. So we use Big O simply for the fact that you may realize that O of f of n is exactly the same of O of 1/2 f of n, right? So let's say you double your computing power. You go switch from 32 bits to 64 bits. A 64-bit computer, in theory, can do twice as many things as a 32-bit computer, band for band, instruction for instruction. One can operate on 64 bits in a single step. The other one, to operate on 64 bits, must use 2 steps. One on the first 32 bits, and then one on the second 32 bits, right? So switching to 64 bits, which I don't know if you guys were born when we did this. This was like 2014. We had 32-bit computers and we had 64-bit computers. Doubled effectively all the programs. But it didn't double any of the algorithms because we only measure things in terms of big O. So that's a different problem. That's an engineering problem, which is not the problem that we study, right? Big O is good because it hides the parts that we don't care about. That's sort of the motivating thing. Any questions on big O? You guys may know that there's 4 other symbols. What are they? Theta? No. Omega? These have very formal definitions, but I'll give you the high-level, easy way to understand them. What are the other symbols? Does anyone know? Yeah? Little o? Yeah? What else? Yes. Little omega? Any others? Theta. Now these have very formal definitions, but I'm going to give you kind of the more useful, intuitive ones. If big O means f of n is less than or equal to cg of n, big omega here means greater than or equals to. So theta is in fact a lower bounds argument. We'll have one lecture on lower bounds, and then we'll have a unit on NP completeness on quote-unquote lower bounds. But basically, to show an upper bound on a problem, you just give an algorithm. To show a lower bound, you have to prove that for every possible algorithm, none can do it in fewer steps. It's much harder to demonstrate a lower bound. What are some lower bounds you guys know? You should learn at least 2 by at this point, I think. Yes? O of 1 is a lower bound on what problem? Every problem. Actually, yeah. Every problem takes at least constant time. Some problems take more, though. What's a better lower bound on any problem you know? Yeah. Yes. We'll prove that later. Anything else? Yes. Oh, yes.
Log n for searching,
Yeah. In what kind of searching?
in a sorted,
Binary search must take at least log n steps. Anything else? Yes.
I guess it's also n for an unsorted list.
Yes. And in fact, most algorithms have a lower bound of linear time. Why? If you take more than that, if you take less than linear time, then you don't need to read the whole input. Think of it that way, right? Why does binary search work? Binary search works because you're promised that the input is sorted. If you have to first check that the input is sorted, that takes at least linear time. So because you're promised the input is sorted, you don't have to read every element. You can kind of jump around and just find the one you want. But if anything that requires you reading the entire input has to take at least linear time. So most algorithms require you to read the whole input. So everything usually has a linear time lower bound. Binary search is an exception, right? Any other lower bounds you guys can think of? The room is quiet because there shouldn't be a single other lower bound you guys can think of, because there aren't any. We don't, as a community, theoretical computer scientists have completely failed to prove lower bounds. Proving an upper bound is easy. How many upper bounds do you know? Like thousands, maybe. I mean, you could, if you asked, it's gun in your head, you could probably figure them out. Every time you give an algorithm, that's just an upper bound. How do you give a lower bound argument? It's very difficult. You have to show for every algorithm, none of them can solve it faster than this. They all must take this minimum number of steps. As a community, theoretical computer science people have failed to prove lower bounds effectively. We don't have any lower bounds for like any problems. In the undergraduate curriculum, these are the only lower bounds you'll ever learn. Like maybe something obscure in graduate school or something, but we can't even prove certain problems require like n to the 1.1. We can't even do that. We have no idea how to do any of this. There are relations to this question to the P versus NP question, but it's basically like why we don't deal with why you never really deal with the omegas. You deal with the O's. We'll talk about that later. We'll have a lecture on that. Right. Anyone remember what little o means? Little o means strictly less than. So less than, but not equal to. So f is never little o of f. It's always strictly less than this. Little omega is exactly what you might think it is, strictly greater than and not equal to, right? And then theta is just equal to, which is f is O of g, and f is omega of g, right? So if some problem is of theta, it's basically like solved. You know you can't do any better, and you already also know you can't do any worse. You have done exactly what you think it should take, right? Right, any questions on big O? Yes?
So in what context would you use the other one?
They come up in contexts that are not really algorithms, but you need to know what they mean. For example, suppose you were given an algorithm that had a runtime of this. What do you think that means? By the way, big O notation often abused. So it may not be as formal as you'd like, but what does that mean? Yeah. Okay. Yes.
So it's greater than constant time? So,
On the exponent.
so
That means we have no clue.
Not quite. We have a little bit of a clue.
More than linear?
What about n squared? Is it more than n squared?
it's exponential.
Not quite. You're almost there.
More than polynomial.
Yeah. So there's a slight difference between exponential and more than polynomial. This exceeds, if you have a runtime of this, it means it exceeds every polynomial. Because you could put, for every constant c, you could put like 10 there. So then that algorithm would take longer than n to the 10. So this means exceeds polynomial. You could also write polynomial as n to the o of 1, because that is technically a polynomial runtime. It's less useful because you don't know what the constant is, and we actually do care about n squared versus n cubed. But that also means polynomial time. What about 2 to the log of n? How much time does that take? Yeah? Yeah, that's linear. That's easy. Okay. What about 2 to the o of log of n? Yeah? Nope. Yeah. It's also not quite exponential. It's polynomial. Why? Yes? Well, you're out of options, so yes. Big O, there's a constant here. Some constant. So this is like 2 to the c log of n, which you know is 2 to the log of n to the c, which is just n to the c. Right? I'm just giving you things that you'll never see, but you should know how to read in case it comes up, because that's what this class is, right? I'll give you one more, and then we can take a quick break. Consider, let's say, 2 to the log of n, and that is to the 1 plus epsilon for some epsilon which is greater than 0. Right. First off, if epsilon is 0, what is this? Yeah, it's just linear if epsilon is 0. What if epsilon is not 0, though? What if epsilon is like 1.1? Make conjectures. Let's hear guesses. Good guesses. Yes? It's not, in fact, this is why it's a good example. It's not polynomial. Yes. It's also not exponential. Now, why? It's kind of weird. It sits between, the reason I'm mentioning this is just so you know if you see this word, it's called quasi-polynomial. It sits strictly between exponential and polynomial. And there are 2 algorithms, at least, that have a runtime that is like this, and we don't know how to improve it. But it's less than exponential, asymptotically so, but it's also greater than every polynomial. I'll leave it to you as an exercise to prove it's greater than every polynomial. Assume to the contrary it's bounded by a polynomial. Do some math. You'll get that n is bounded by a constant, something like this. And then assume it's lower bounded by an exponential. You'll get a similar argument as well. So there are some weird and crazy things that you can that are out there when you play around with big O. And I won't say for certain that everything will look like one of the few things that we know it should, right? What are the common runtimes? Forget the extremal adversarial cases of runtimes. What are common runtimes you've seen of algorithms, like the good stuff? What's the fastest algorithm you've ever seen? What's the runtime of that? Yeah, so O of 1. What's the next fastest runtime you've made that's common? Yeah, log n. You could say log is faster than log, but there's not many problems you could say take log that you should have seen, right? What comes after log? O of n. O of n log n. What else? Yeah, n squared. What else? Yeah, you could technically say n squared log n. That's not as common. But then you could say n cubed. And there's a couple basically, in practice, anything after n cubed is pretty bad. But sometimes there are only things that we have that are n cubed, so we just kind of stick with them. And we don't know how to improve them past n cubed. But there are some things that are not nice. We mentioned this is a quality polynomial, but it doesn't really show up. Exponential runtime could be 2 to the n. And then what are some things that exceed exponential? N factorial is another runtime. And there's one that exceeds that. Yeah. And of course, there are exotic things that even grow way past that. N to the n to the n, n times, and so on, right? 2 to the 2 n times, in fact, exceeds that. So, right, any questions? All right, let's take a break.